Students are requested to drop down their names for attendance purpose. Students can drop down their names for attendance purpose. We'll be starting in a while. Meanwhile, you can drop down drop down your names. You can drop down your names for attendance purpose. We'll be starting in a while. Okay, good. So I think we should start now. So we were previously discussing about the p block elements, and we had done the physical properties about the 15th group basically, and now we will discuss the compounds that are made by the 15th group. Compounds that are made by the 15th group. So what all are elements there in the 15th group? That is the nitrogen, phosphorus, arsenic, tritium or antimony, and bismuth. Right, so these are the elements that are present in the 15th group of the p block. Why do we call these elements as p block elements? Because the last electron in these elements enters the p orbital, therefore they are known as what? P block elements. Okay, so now we have to discuss about the hydrides of group 15, right? So all the elements of group 15 form hydrides of the type EH3, where E is what? Basically E is the 15th group element. For example, NH3, PH3, ASH3, SBH3, right? So all elements of group 15 form hydrides which are of the formula EH3. So the stability of the hydrides decreases from NH3 to BiH3. That means the stability will decrease down the group. Why it is decreasing? Because their bond dissociation enthalpy is decreasing. See here, the bond dissociation enthalpy for NH3 is 389, PH3 is 322, arsenic it is 297, then for antimony it is 255. So here you can see that the bond enthalpy is decreasing, and we already know that bond dissociation energy or bond dissociation enthalpy basically is directly proportional to the bond strength. is directly proportional to the bond strength. That means lower the value of bond dissociation enthalpy, that means weaker is the bond and lesser is the stability, because it will break with a minimal amount of supply of energy. Okay. So, reducing character of the hydrides increases down the group. Now, basically what is a reducing agent, right? If you see as reducing agent is what basically which delivers H minus, right? Am I correct? Reducing agent is basically what which delivers H minus. In organic also you must have studied that AlH4 minus or BH4 minus, they are acting as reducing agent because they deliver H minus, right? So reducing character of the hydrides increases down the group. That means ammonia, if you see, it is a mild reducing agent, while the hydride of bismuth, if you see, it is the strongest reducing agent amongst all the hydrides, right? So obviously, this can be also understood on the basis of the bond dissociation enthalpy. For ammonia, if you see here, the NH bond is having a greater bond dissociation enthalpy, so it will not release H minus particularly, right? Because there is a strong bond formed between nitrogen and hydrogen. While in case of bismuth and hydrogen, if you see, it can release H minus easily. Why? Because the bond dissociation enthalpy is very less, and therefore it can release H minus, and therefore it can act as a good reducing agent also. Okay. So, next if you see, basicity decreases in the order. What are Lewis bases and Lewis acids? Lewis acids are what? Which are electron deficient in nature, while Lewis bases, if you see, they are electron rich in nature. For example, the compounds which are having lone pair of electrons are termed as Lewis bases because they are having a lone pair of electrons, they are having greater electron density. Right. So, if you see the basic nature, ammonia is basic, then phosphine, then arsenic, then antimony, and then bismuth, right? Why this? Because here what happens is, for example, if you see in ammonia, the lone pair of electrons, right? Because nitrogen is electronegative, right? It keeps the lone pair of electron towards itself, but as we know that down the group electronegativity decreases, right? So the lone pair here, that is of phosphine or arsenic or antimony or bismuth, basically the lone pair is delocalized over the all molecule, right? So where there is a delocalization of the lone pair of electron, that means they are not available for donation. But in case of ammonia, if you see, the lone pairs, because of the greater electronegativity of nitrogen, they are not delocalized, rather they are situated on the nitrogen itself, right? So they are available for donation because they are not delocalized over the whole molecule, while in case of others there is delocalization of the lone pair of electrons amongst all the the whole compound, basically the whole hydride compound, therefore the basicity decreases. Okay, so I hope I am clear. Now next, if you see, ammonia is hydrogen bonded, right? Because for hydrogen bonding there are two conditions. What are the two conditions? That first sorry, that first there should be a electronegative atom present, and second, a hydrogen must be attached to it, right? For example, if you see water, oxygen is an electronegative element, hydrogen is attached to it. For ammonia, if you see, nitrogen is an electronegative element and hydrogen is attached to it. So ammonia and water both show hydrogen bonding, right? Due to which what happens is that its boiling point and melting point is very high. While other hydrides, if you see, because they are lower in electronegativity, because phosphorus, arsenic, antimony and bismuth, if you see, they are not that much electronegative than that of the nitrogen, so they do not involve hydrogen bonding, and boiling point now depends upon the mass. I have already told you that boiling point depends on the molecular mass. So down the group what happens is, down the group molecular mass increases, therefore boiling point also increases, while the melting point will depend upon the structure of the compound, basically, right? So NH3, in spite of having the lowest boiling point, it is having the highest boiling point because of the intramolecular hydrogen bonding. Okay. Now here if you see, this is also very important. The bond angle in ammonia, if you see, it is 107.8 degree, indicating that it is sp3 hybridized. That means it is having a tetrahedral geometry, right? So if you see nitrogen in ground state, what is the configuration? 2s2. 2p3. Okay, so what happens here is that the electrons from hydrogen resides here, right? These are the electrons of hydrogen basically, and this is the lone pair of electron. So you can draw the structure of ammonia like this, right? See, the actual angle of tetrahedral should be 109 degree 27, right? But here what happens is that due to lone pair bond pair repulsion, the size decreases. There is a repulsion here, so the angle gradually decreases. This particular angle decreases to 107 degree approximately. Okay, so the angle is less than that of the ideal tetrahedral angle value. For other compounds, the angles are close to 90 degree, right? This is because why? The decrease in bond angle is attributed to the increase in bond length, thereby reducing the extent of lone pair bond pair repulsions. Now this is also very important. See, what is happening here is that if you take, let us say, phosphorus, or if you take arsenic, or if you take antimony, basically because they are larger in size than that of the nitrogen, they are having what? Longer bond lengths between phosphorus and hydrogen, or arsenic and hydrogen, or antimony and hydrogen. So what happens here is, because of the longest bond length, they are having less bond pair lone pair repulsion down the group. Okay, so you can apply just Drago rule to phosphine, arsenic and antimony. You can apply Drago rule to them, Drago's rule, right? So for such compounds, what is happening here, that the angles are close to 90 degree. Okay. Now next, if you see, question is, why does group 15 hydrides act as a Lewis base? So group 15 hydrides act as a Lewis base. Why? Because they are having one lone pair of electrons on central atom which are available for donation. For example, if you see NH3, lone pair of electrons, PH3, lone pair of electrons. So because of the availability of lone pair of electrons, they are acting as a Lewis base. Question is, explain why the dipole moment of hydride is of the order. See, dipole moment is basically what? It is basically depending upon the electronegativity of the element, right? So here if you see what, that nitrogen is very electronegative, so it will tend to attract the electron density towards itself, and the resultant dipole will come out to be this. But in case of PH3 or arsenic hydride or antimony hydride, or if you see bismuth one, what is happening here is that when you go down the group, the electronegativity of the central atom decreases, right? Here if you see, electronegativity will decrease, so it will not pull the electrons, the shared pair of electrons between phosphorus and hydrogen towards itself to such an extent in which as compared to that of the nitrogen and hydrogen basically, right? So phosphorus, due to the lesser electronegativity, it will have a lesser dipole moment. Then arsenic, much lower electronegativity. Tritium, if you see, much lower electronegativity, and bismuth, the least electronegativity amongst the whole group, right? So this is why the dipole moment of hydrides is of the order this. Okay. So yeah. Moving on next to the oxides. So all these elements commonly form two types of oxides, that is E2O3 or E2O5. For example, N2O3, N2O5, or P2O3, P2O5, right? So these are the basic general formulas for the elements of group 15. So the oxide in the higher oxidation of the oxidation state of the element is more acidic than that of the lower oxidation state. That means what? Here if you see the oxidation state of E, basically that is the element here for the P block, it is having +3 oxidation state, and here it is having +5 oxidation state, and we already know that more electron deficient, that means more acidic. So here you can see that higher oxidation state will have more acidic character than that of the lower oxidation state, right? Now second thing is, here is their acidic character decreases down the group. Acidic character decreases down the group. Now this can also be explained on the basis of the metallic character. If you see, we already know that down the group what happens, that metallic character increases. That means what? That the elements which are present at the downwards, or basically the heavier members of the group 15 element, like bismuth, they tend to donate electrons, right? They tend to donate electrons, and acid is what basically, which is electron deficient, it likes to accept electrons rather, right? So therefore the acidic character decreases down the group. Now the oxides of the type E2O3 of nitrogen and phosphorus are purely acidic. That means what? N2O3 and P2O3 are very acidic. But while in case of arsenic and antimony, if you see, that means As2O3 and Sb2O3, if you see, they are amphoteric. That means they can behave as base also and as acid also, while bismuth, if you see, because it is a pure metal, right? So its oxide is what? Basic in nature. Its oxide is basic in nature. We have already studied that non-metal oxides are acidic in nature, while metal oxides are basic in nature, right? So here if you see, nitrogen and phosphorus are pure non-metals, therefore they are acidic, they are forming acidic oxides, while in case of bismuth, if you see, they are forming basic oxides, right? While the other two are forming the amphoteric oxide, which can behave as acid also and which can behave as base also. Now coming on to the halide compounds, so they generally form trihalides or pentahalides. Basically what? We already know NCl3, right? Or we are knowing PCl3, PCl5, right? ASCl3. ASCl5. So these are the particular trihalides and the pentahalides that are formed by the group 15 elements. Nitrogen does not form pentahalide. This is very important. Why does it not form pentahalide? Because it can have a maximum covalency of 4 only, right? It can possibly make only 4 bonds. It does not have vacant d orbital in which it can accommodate the extra electrons, so that it cannot expand its octet basically, and therefore it cannot form pentahalide, while all the trihalides of these elements except those of nitrogen are stable. Now this is very important. If you take PCl3, if you take ASCl3, if you take SbCl3, or if you take bismuth Cl3, they all are stable, but if you take NCl3, they are not stable, while the only trihalide which is stable for nitrogen is NF3. Okay. Trihalides except BiF3 are predominantly covalent in nature. Now this is very important. How can you define basically the covalency of the compound and the ionic nature of the compound? That greater the electronegativity difference, more is the ionic character. So here if you see, let us say BiF3, so this is a metal, right, and this is a pure non-metal, right? So fluorine is having a very high electronegativity, while bismuth is not having high electronegativity as because it is a metal in nature, right? So we are already knowing that generally if you have metal and non-metal combined, in which there is a electronegativity difference, there is a considerable electronegativity difference, that will form a ionic compound, that will form a ionic compound, right? So bismuth is the least electronegative amongst the group 15 element, while fluorine is the most electronegative element in the periodic table. So they both are forming ionic compound, and the rest of the trihalides are covalent in nature. They are covalent in nature. Now this is the question, why are pentahalides more covalent than that of trihalides? For example, let us say that PCl5 we are taking and PCl3 we are taking. What is the oxidation state of phosphorus? +5. What is the oxidation state of phosphorus here? +3, right? And according to Fajan's rule, what we have studied, that smaller the cation, larger the anion, greater is the covalent character. Greater is the covalent character. Right. So here if you see, obviously phosphorus with a +5 charge will be more smaller as that of compared to phosphorus with a +3 charge. So what will happen here, that smaller the cation, anion is the same only, right, chloride and chloride, it is having a -1 charge here also, -1 charge here also. But if you see the oxidation state of phosphorus, it is different in both, right, one is having +5 and one is having +3. So we are knowing that phosphorus in fifth oxidation state, that is +5 oxidation state, is lesser in size as that of the phosphorus in third oxidation state, right? So this means what, that smaller the cation, greater is the covalent character. Therefore pentahalides are more covalent than that of the trihalides. Is it clear? Is it clear till now? Guys, is it clear till now? I hope you remember Fajan's rule. Okay, good. This we have already discussed about the Fajan's rule. Though nitrogen exhibits +5 oxidation state, it does not form pentahalide, right? See here that the oxidation state means that you have removed 5 electrons from nitrogen basically, right? But the covalency, that is the number of bonds that are formed by nitrogen basically, cannot exceed 4. It can form only 4 bonds, right? So therefore it does not form pentahalide. Do not confuse oxidation state with covalency. Or basically do not, okay Sham, I'll explain this question again. See here, Fajan's rule explains that smaller the cation and larger the anion, greater is the covalent character. So we all know that as the positive charge on the ion increases, there is a decrease in size. For example, let us say there is an element X, right? So X plus will be smaller than that, X2 plus will be smaller than that, X3 plus will be smaller than 3 of them, X4 plus will be smaller than 4 of them, right? So what does this means? That in phosphorus pentahalides, if you see, let us say PCl5 and PCl3, here the oxidation state of phosphorus is what? Basically +5, है ना? And here the oxidation state of phosphorus is what? +3. So phosphorus +5 will be smaller than that of phosphorus +3. This means what? That the size of the cation in case of pentahalides is smaller than that of the size of the cation in case of trihalides, and we already know that smaller the cation, greater is the covalent character according to the Fajan's rule. So here if you see, P plus 5 is smaller than that of P plus 3, and therefore it is having a more covalent character. Is it clear now? Is it clear now? Okay, good. So next if you see, so don't confuse basically nitrogen's oxidation state to its covalency, right? Nitrogen has s and p orbitals only in the valence shell. It does not have d orbitals. So basically it cannot form bonds beyond 4. It can only form maximum number of bonds, that is 4, right? So +5 state is the oxidation state. That does not mean that it will form 5 bonds. So this particular thing people get confused with, that oxidation state equals to the number of bonds formed. No, oxidation state only says that how many electrons have been removed from that particular element, but covalency is the amount of, or the number of bonds that are formed by that particular element. Now reaction with metals. Now this is important. See, all these elements react with metals to form their binary compounds in +3 oxidation state. For example, if you see it, the nitrogen will combine with calcium to form calcium nitride, right? Phosphorus will combine with calcium to form calcium phosphide. Arsenic will combine with sodium to form sodium arsenide. Okay, antimony will combine with zinc to form zinc antimonide, and bismuth will combine with magnesium to form magnesium bismuthide. Now we'll study about dinitrogen. So dinitrogen, if you see, that is N triple bond N, or we term it as N2, that is present in our atmosphere with a percentage of 78%. So it is a colorless, odorless, tasteless and non-toxic gas. It has 2 stable isotopes. Basically nitrogen has 2 isotopes, N14 and N15. What are isotopes? Basically which are having same atomic number but different mass number, right? So it has a very low solubility in water. Why it is having a low solubility in water? If you see here that N2 is a non-polar gas, right? It is a non-polar gas, while water, if you see, it is a polar solvent. So what will happen? that like dissolves like. So non-polar will not be dissolved in polar solvent, therefore it is having a low solubility in water, and it is also having low freezing and boiling points. So except nitrogen, all the other elements, as we have seen that phosphorus was having white phosphorus, red phosphorus, black phosphorus as allotropes. So except nitrogen, all the elements of the group 15 are showing allotropy. Nitrogen differs from the rest of the members of this group due to its smaller size. Now this is very important. This is the anomalous behavior that is shown by the second period element in their respective groups, right? So reason is the same for all the groups, that why the particular first element is showing different properties rather than that of the other elements, because the second period elements have smaller size, they are having high electronegativity, high ionization enthalpy, and they don't have vacant d orbitals, or they basically don't have d orbitals in them, right? D orbitals are not present in the second period elements, therefore they differ from the rest of the elements in their respective groups. Now this is also very important, as we have seen that carbon is having a catenation property, that means it can form bonds with itself, right? Longer chain bonds with itself. Similarly silicon also, if you see, it is forming catenation property, but here if you see that nitrogen is having a very less catenation property, right? Because nitrogen bond is weak. Can you see here? Nitrogen bond is weak. Here you see bond dissociation energy of carbon bond is 355.3, while in case of nitrogen, if you see, it is 163.8. Okay, so phosphorus, arsenic and antimony form single bonds, that is PP, arsenic, antimony, while bismuth is metal, so it forms metallic bonds in its elemental state. Now see here, the nitrogen bond is weaker than that of the PP bond. Why? Because if you see that nitrogen is a electronegative element, right? So what will happen here, because, and also it is very small in size, so what will happen here, that when it will form bond, the lone pair of the electrons that are present on it, gradually they will repel each other, right? So because of this repulsion, the catenation tendency is weaker. Nitrogen bond are very weak. Because of the small size, the electrons are having high repulsion, while in case of phosphorus, if you see, they are having a little bigger size than that of the nitrogen, and therefore the interelectronic repulsion between the two phosphorus is not as much as that of the nitrogen. Okay. Now less reactivity of N2 gas. See, N2 gas, if you see, it has a unique ability to form p-pi multiple bonds. That we already know that N2 is making what? P-pi multiple bonds. That means it is having a triple bond between two nitrogens. And also with other elements, if you see, nitrogen forms C triple bond N, right? Or isocyanide is also there, NC is also there, right? So basically, if you see that, it forms p-pi multiple bonds because of the small size and high electronegativity. If you see here, carbon also, oxygen also, they also form bond with or multiple bond with nitrogen. So the elements which are having small size and high electronegativity can form bond with nitrogen, in fact multiple bonds with nitrogen, like in that of the cyanide group. Okay. Now heavier elements of this group do not form p-pi bonds, right? Why they cannot form p-pi bonds? Because of the larger size, they are having their atomic orbitals are so large that they cannot diffuse into each other and cannot have effective overlapping. Okay. So nitrogen exists as a diatomic molecule with a triple bond, that we have already done, and the N2 molecule, if you see, the bond dissociation energy is 941.4 kilojoule per mole, right? So which makes it as less reactive as that of the noble gases. We know that noble gases are very inert in nature. Similarly also, if you see that N2 gas is very stable in itself, right? And therefore in organic chemistry also, if you will see that N2 is a very good leaving group because it is stable in itself. Okay. Now due to the absence of d orbitals, covalency of nitrogen is only 4. That means what? That nitrogen can form a maximum of 4 bonds only, right? Now it is very important that because of the absence of d orbitals also, it cannot form d-pi bond, while the heavier elements, if you see here, they can form d-pi bond, right? So this type of bond, if you see that, they are d-pi bonds, d-pi bond, d orbital from the phosphorus and p orbitals from the carbon itself, right? So phosphorus and arsenic cannot form d-pi bond, can form d-pi bond also with transition metals. So here if you see that compounds like this, right, they act as ligands. In coordination chemistry we will learn that. For example, let us say chromium is here, it will use its d orbital, and this particular compound of phosphorus will also use its d orbitals, and they will form a type of a d-pi bond. So such compounds are known as what? The coordination compounds, right? So basically these compounds, phosphorus and arsenic, if you see, compounds of such type of phosphorus and arsenic, they can also behave as ligands. That we will learn in the coordination chemistry, that what are ligands, how a d-pi bond is formed. Okay, so that is a part of coordination chemistry. Now preparation of nitrogen, if you see in the laboratory, dinitrogen is prepared by treating an aqueous solution of ammonium chloride and sodium nitrite, right? So if you treat ammonium chloride with sodium nitrite, it will give you a N2 gas plus water plus NaCl in the aqueous form, right? And small amounts of NO and HNO3 are also formed in this reaction. These impurities can be removed by passing the gas through aqueous sulfuric acid containing potassium dichromate. It can also be obtained by the thermal decomposition of ammonium dichromate, right? So this particular thing, you can remember that ammonium chloride plus NaNO2 gives N2 plus H2 plus NaCl, and the second way to produce the nitrogen gas is that the decomposition of ammonium dichromate will give you nitrogen gas, right? Similarly, here also, if you heat barium azide, basically you can get barium plus nitrogen gas. So these are the preparation of the nitrogen gas, that basically in the laboratory, how can you prepare the nitrogen gas. So dinitrogen is produced commercially by the liquefaction and fractional distillation of air, right? So what is fractional distillation? You must have learnt in your 11th class also. So liquid dinitrogen is having a boiling point of 77.2 Kelvin, and it distills out first, leaving behind oxygen, which is having a boiling point of 90 Kelvin. Because it is having a lower boiling point, so it distills out first, and therefore we can separate basically dinitrogen and oxygen, right, from the air by doing the fractional distillation of air. And one thing is there which is known as the liquid nitrogen. Basically it is so cool in nature. If you put your finger into that particular liquid nitrogen, what will happen? Your finger will just crisp out and break, right? So it is so strong. Now dinitrogen is rather inert at room temperature because of the high bond enthalpy of N2 bond, right? You are already studying that it is very inert, and the bond dissociation enthalpy of N2 bond is also very strong. So if you say that reactivity, however, increases rapidly with rise in temperature, right? So when you will increase the temperature, it will start reacting. Okay, at higher temperature, it directly combines with methyl. For example, if you see that lithium is combining with nitrogen, you must have learned this in your S block in 11th class, that lithium is the only metal which is, lithium and magnesium basically are the only metals which are combining with nitrogen, right, to form ionic nitrides like lithium nitride or magnesium nitride. Okay. Next, it's a very important process of dinitrogen, that is dinitrogen combines with hydrogen, which is known as Haber's process, to give ammonia gas. Okay, so dinitrogen combines with dioxygen at a very high temperature, at about 2000 Kelvin, right, to form what? Nitric oxide. So this Haber's process is very important from the examination point of view. See, you don't have to learn each and every equation, right? Equations are not that much important in this chapter. Rather, we will give you a short summary of equations that you need to learn. For example, the Haber's process, if you see, right, that is an important one. So you don't have to mug up each and everything. Rather, focus on the questions such like why this is happening, how this is happening, why it is having a lesser basicity, why it is having a more acidic character, right? Focus on these type of questions more, right? And also the things which are basically, you know, a part of mugging up basically. For example, if you see here, the greatest use of nitrogen in ammonia is in ammonia, which is used in a fertilizer production, right? So basically in competitive examinations, especially in IIT JEE, mains and advanced paper, you will be not asked such questions more frequently that are basically a part of mugging up, right? So focus on the part that is considering the reasons basically that why this particular thing cannot happen, how this particular thing is taking place, right? So don't get basically what we do at the end, we just leave such kind of chapters, right? So don't do it, rather focus on some things which are very important. Don't mug up the whole chapter, just read out NCERT 2 to 3 times. NCERT is more than sufficient for this particular chapter, and then figure out that what things are important. Structures are important. For example, the structure of phosphorus, if you say allotropes of phosphorus that we have done, they are important, right? And in the upcoming sessions also we will be discussing some structures such as S8 structures. So these structures are important, right? So you can just learn these structures here, the reasoning questions here, reasoning questions, some important reactions, only some reactions, right? Not all reactions, because if you look at NCERT, there are a minimum of I guess 50 to 60 reactions. You don't have to mug up all the reactions, right? So focus on structures, reasoning questions, and we will provide you a short list of reactions that you have to learn. And yeah, that's and uses, if you see, there are only a particular use that you have to remember. For example, N2H4, if you see, it is used as a rocket fuel. So such questions can be asked, right? So there are particular uses that you have to learn. You don't have to mug up whole the chapter. Okay, so don't do the mistake of leaving the whole chapter, right? If you are not mugging up the equations, don't leave the whole chapter. At least focus on the main points or the frequently asked questions from this chapter. Okay, so let's come back to our session. Uses of nitrogen, if you see, the greatest use of nitrogen is in ammonia. So ammonia is basically used as a used for fertilizer production, right? And it is also used for the production of nitric acid, that is HNO3. So nitrogen gas is used where inert atmosphere is needed. For example, if you see that we are performing certain reactions, right? And that particular product, if you see that it reacts with atmosphere and get decomposed. So what we will do in place of that, we will provide a nitrogen gas atmosphere, because it is inert, so it will not react with our compound. Okay. So in laboratory also, to provide an inert atmosphere to certain reactions, we use nitrogen gas. Okay, so in iron or steel industry also, or ordinary light bulb, if you see, or the packet of chips, right, to provide rancidity, to prevent rancidity, basically liquid nitrogen gas is also filled in the packets of Lay's, Kurkures and all, right? So nitrogen is also used in protecting historic documents, right? Because it is inert in nature, to provide the oxidation of papers, basically nitrogen is used there, right? So liquid dinitrogen is used as a refrigerant. For example, that ice creams and all, right? Can you see the smoke coming out? It is of liquid dinitrogen only, and it is so cool that I have already told you that if you put your finger into that, it will just crisp out and your finger will break from that part. Okay. So it is also used to preserve biological materials, food items, and in cryosurgery. Okay. And also it is used to preserve ice creams, basically to avoid melting of ice creams. Now next we will discuss hydrides in details. So hydrides, if you see, all elements of this group from gaseous hydrides of the type MH3. That means what? That ammonia, phosphine, arsine, stibine, bismuthine, all are gaseous hydrides, right? Now the stability, however, decreases down the group for these hydrides that we have already done, that the bond dissociation enthalpy, if you see, there is a decrease in the bond dissociation enthalpy, and therefore the stability also decreases down the group. So all the hydrides are strong reducing agents because they can deliver H minus. Okay. Phosphine and other hydrides of heavier member of these groups are highly poisonous. So these particular, if you see, these particular hydrides, they are highly poisonous. Highly poisonous. Okay. Hydrazine, if you see, it is another important hydride of nitrogen. Now this is important, as I have told you that hydrazine is used as a rocket fuel basically. So this particular thing you can remember about hydrazine. Now the preparation, if you see, calcium nitride if treated with water, or calcium phosphide if treated with water. So if you will treat nitride with water, you will get ammonia. If you will treat phosphide with water, you will get phosphine, right? And here if you are taking the compound which is made up of zinc and basically the M, where M is what? Arsenic, antimony or bismuth, you can get the typical hydride. Okay, for example, Zn3 As2 plus HCl will give you what? AsH3, right? Similarly, if you see Zn3 Sb2 in the presence of HCl, it will give you what? SbH3. Okay, now hydrazine can be prepared by the action of ammonia and sodium hypochlorite. So sodium hypochlorite plus ammonia will give you what? Hydrazine. Okay. Now this is important, this you have to answer. Which of the following is or are not known? This you have to answer. Provide the answer for this particular question. It is very easy, we have discussed. Provide the answer for this particular question. What should be the answer for this particular question? It is very easy, just focus on the options. That which one is not possible? Formation of which is not possible? Anyone with the answer? Anyone with the answer for this particular question? Okay, Shivranjani is saying NCl5. What about others? What about others? I have already explained that a maximum number of bonds that can be formed by nitrogen is only 4. It cannot form 5 bonds, right? So Shivranjani, good, you are correct with the answer that NCl5 is not known. But except NCl5 also, there is also a compound which is BiCl5, right? That is the chloride of bismuth basically, right? So here if you see that Bi5 plus being an oxidizing agent, what does it do? That it just oxidizes Cl minus to chlorine and it reduces itself from 5 plus to 3 plus because of the inert pair effect that we have already done. So what happens is that BiCl5, if you see, it will just decompose to chlorine and bismuth 3 plus. Okay. So BiCl5 and NCl5 cannot be formed. Yeah, Arun, Shri Harimurthy, Tasneem, you also are correct with your answers. Now summary properties we will see. Central atom assumes sp3 hybridized state. We have already done that. NH3, if you see the hybridization, basically it is sp3, right? Tetrahedral. Similarly for pH3 also, SbH3 also, arsenic H3 also, right? Bond length increases down the group because of the increase in the size. For example, if you see nitrogen and hydrogen, both are smaller, so the bond length will be shorter. While in case of phosphorus and hydrogen, if you will see, phosphorus is a bigger atom, so the bond length will be larger than that of the nitrogen hydrogen bond. This we have discussed. The group thermal stability decreases, bond angle decrease down the group. We have done that. Phosphine, arsenic and The lower members form the basically have 90-degree angle because of the Drago's rule, right? Boiling point of hydrides increases from pH3 to BiH3, but NH3 has exceptionally high boiling point because NH3 is showing intermolecular hydrogen bonding, and for pH3 to bismuth H3 you can just follow the trend that increase in the molecular mass, increase in the boiling point. So they are acting as Lewis bases and the basic character decreases down the group. This we have also done, that why the basic character is decreasing down the group because of the delocalization of the electrons. So we will discuss the hydrides one by one. So nitrogen is known to form 3 different hydrides, that is ammonia, hydrazine and hydrozoic acid, right? So ammonia is a very important hydride if you see. So one process we have seen, that how can it be formed by the Haber's process. N2 plus 3H2 will give you what, 2 ammonia. By Haber's process it can be formed, or by basically treating urea with water. It is forming ammonium carbonate first and then ammonia can be formed. The methods of preparation, on a small scale if you see that ammonium chloride on treating with calcium hydroxide, ammonia will be formed, right? Ammonium sulfate plus sodium hydroxide, ammonia will be formed. Or if you are taking, let us say, aluminium nitrate, when you react it with water, it will form what? Aluminium hydroxide plus ammonia. Haber's process, this you have to study in detail because it is very important. This method involves the direct combination of basically nitrogen and hydrogen to give ammonia, right? But because it is also, dinitrogen is very inert in nature, so it is having very harsh conditions. This reaction is having very harsh conditions. So the temperature is around 700 Kelvin and pressure of around 200 atmosphere is taken, right? And we also use catalyst to basically speed up the reaction, like molybdenum. So finely divided iron with some molybdenum as a promoter we can use because it is increasing the surface area if you see, and finely divided iron with aluminum oxide and potassium oxide can also be seen, right? Okay. So these are the catalysts basically. Here if you see that hydrogen and nitrogen are in the form of gaseous form. So we supply it to it and the compressor turns it into the liquid form basically, then you provide the catalyst here and then it will lead to the production of ammonia basically, okay. Now see the physical properties. Ammonia is a colorless gas with a pungent odor. Ammonia molecule is trigonal pyramidal. Why it is pyramidal basically? Because if you see the geometry, if it is tetrahedral in nature, but in case of shape, when you have to tell the shape, you have to ignore the lone pair of electron, therefore it is pyramidal in nature, right? Its freezing and boiling points are 198.4 and 239.7 Kelvin, which you don't need to remember at all. In the solid and liquid states, it is associated through hydrogen bonds. This we have already done, that it shows hydrogen bonding as in the case of water also, right? So because of the hydrogen bonding, it accounts for the high melting point and the boiling point of ammonia as well. So it is soluble in water due to hydrogen bonding. It is soluble in water due to hydrogen bonding. So if you treat ammonia with water or dissolve ammonia with water, basically what we get? NH4OH. NH4OH. Ammonium hydroxide. Now chemical properties, if you see, combustion of ammonia will give you what? Nitrogen plus water. Now basic nature we have already done, that it is a Lewis base and basically it attacks on the acid, that is the H plus, and forms the ammonium ion NH4 plus. NH4 plus. Now this is also very important. This is important, especially this reaction. Ammonia donates the lone pair of electron to form linkage with metals ion. Can you see here that ammonia with it lone pair combines with copper 2 plus. So basically it is donating its lone pair of electron and forming a coordinate bond. So this particular thing we will study in coordination chemistry, that what is a coordinate bond or a dative bond basically. So the structure is somewhat like this, that ammonia is donating its electrons toward copper 2 plus and it is forming a deep blue complex of copper. Similarly, it can be detected for silver also, that if you treat silver chloride with ammonia, you will get such type of complex. Similar type of complex was also there in the that Tollens reagent, if you remember. So this is how you can basically detect copper and silver from ammonia. Reactions of aqueous ammonia, if you see, if you treat ferric chloride with ammonium hydroxide, you will get what? Fe2O3 dot XH2O, right? That is the basically oxide of iron. And ZnSO4 plus ammonium hydroxide, that will give you zinc hydroxide, which is giving a white PPT, and iron oxide was giving a brown PPT. When we take chlorine in excess here with and treat it with ammonia, basically a explosive substance that is known as nitrogen trichloride is formed. So NCl3 is a very explosive substance, right? And if you basically oxidize ammonia with bleaching powder, you will get what? Calcium chloride, nitrogen gas and water. This is very important. This you have to learn. See, the reactions which are very important, I am already telling you before only, right? I am already making you understand that particular concept, that which reactions are important and which reactions are not important, right? So these reactions, basically the detection of ions is very important, okay? So reaction with Nessler's reagent, right? If you treat Ki with HgCl2, what will be formed here? HgI2. Now again this HgI2 will react with Ki to form a complex known as K2HgI4, or you can also write it as HgI4 2 minus. So alkaline solution of this particular compound, of this particular complex, is known as Nessler's reagent. It is basically used for the detection of the cation, ammonium cation, right? So I think in 12th you must be doing the detection of salts, that which cation or which anion is present in a particular salt. So there we use Nessler reagent, right? So ammonium with reacting with ammonium ion with reacting with Nessler reagent, it gives a brown PPT, and the formula of brown PPT is also very important, that you need to remember. That is NH2HgOHgI. This particular formula also you have to remember, okay? So basically you can use ammonia to detect the presence of ammonium ions in a salt. So this is a particular brown PPT that will be formed here. You will see such color. Now uses of ammonia we have already done. Liquid ammonia is used in refrigeration. Aqueous ammonia is used in qualitative as well as quantitative analysis in the laboratory. In manufacture of nitric acid, that is Oswald process, and sodium bicarbonate, you must have done it in your 11th class, I guess, right? That how can you particularly form sodium bicarbonate through a Solvay process, and ammonium compounds. So that can be manufactured from ammonia, basically like ammonium sulfate, ammonium calcium phosphate can be formed by the help of the ammonia, right? So here also if you see that these compounds basically are used as what? Fertilizers, right? And ammonium nitrate is also used in certain explosives. So two explosives we have studied, that is NCl3 and ammonium nitrate. Also ammonia is used as a cleansing agent for removing basically grease. Ammonia is also used in the manufacture of urea, which is also excellent fertilizer of nitrogen. So what is the formula of urea? NH2CONH2. Now this is very important. The bond angle in ammonium ion is more than that of ammonia. Answer this particular question. This is ammonia and this is ammonium ion. Both are having what? Tetrahedral geometry. Then why the angle of ammonium is more than that of ammonia? Why the angle in ammonium is more than that of ammonia? Bond angle. Let me know the answer. A basic concept needs to be applied here. Anyone with the answer? What should be the answer for this particular question? Questions like these are very important from the examination point of view, right? So don't consider that P block is a mugging up part. Rather, the people who are just making the question paper also know that children cannot remember each and every equation. So the paper is set accordingly. Anyone with the answer? Yes, Shivranjani, very good. Lone pair, bond pair, repulsion. Here if you see that lone pair, bond pair, repulsion is there, while here only bond pair, repulsion is there, right? So we know that lone pair, repulsion is much greater in magnitude than that of the bond pair, repulsion. Bond pair, repulsion. And due to the lone pair, bond pair repulsion, what happens is that the angle here gets decreased, right? The angle here gets decreased because of the lone pair, bond pair repulsion. Very good. So here if you see there is bond pair, repulsion. Here if you see there is lone pair, bond pair repulsion, and we already know that due to lone pair, bond pair repulsion there is a decrease in the angle, right? So henceforth the bond angle in ammonium is more than that of ammonia. What is Nessler's reagent? What is Nessler's reagent? Next question. What is Nessler's reagent? This also we have already done. Answer fast. What is Nessler's reagent? Come on guys, we have already done this only 2 minutes before, I guess. Yeah, Shivranjani, very good. Alkaline solution of K2HgI4 is known as Nessler's reagent. Very good. Now next see hydrazine here. Hydrazine is was basically N2H4. So hydrazine is manufactured by the Racic process, right, in which ammonia is oxidized by sodium hypochlorite in dilute aqueous solution. So here if you see that ammonia is treated with sodium hypochlorite and it is forming NH2Cl plus NOH. So this is a fast reaction. It is happening basically in 2 steps, right? And this particular ammonia will react with now NH2Cl and form hydrazine. Now this process is known as Racic process. Racic process. Okay. So hydrazine is a powerful reducing agent and it is used to prevent the oxidation of the boiler and pipes. Right. The compound and its derivatives are used as rocket fuel. This is important use of hydrazine. And the structure is also very important. Can you see here the structure? Nitrogen is forming 3 bonds, 1 lone pair, 3 bonds, 1 lone pair. So N2H2. Methods of preparation, if you see, what is the laboratory method? So if you take the boiling yellow phosphorus, which is also known as the white phosphorus basically, which turns yellow, we have done in the previous session that why the white phosphorus is also known as the yellow phosphorus, because the freshly prepared phosphorus is white in nature, but after some times it turns into yellow, right, when some impurities are added basically. So when white phosphorus or the yellow phosphorus is treated with the sodium hydroxide in the presence of water, you will get sodium hypophosphite plus phosphine. Okay. Now Phosphorus also forms P2H4 beside PH3. Now this is also very important, that N2H4 we know basically that it is being formed. Similarly, P2H4 is also formed. So phosphine has two laboratory preparation basically. First is this one and the second one is this one, that is treating P4 with the NaOH in the presence of water can give you NaH2PO2 plus P2H4. So this is basically what? This is the preparation for P2H4 and this is the preparation for phosphine. Okay. Now, if you see, when pure it is inflammable but becomes inflammable owing to the presence of P2H4 or P4 vapors. Okay, so I think the time is up. Okay, we will continue in the next session. That is all for today. Okay, we will continue this session afterwards. So, we will be doing about halides and basically more about phosphines, right? So, you can basically, what you can do is that at your homes you can just read the chapter. Read the chapter from NCERT. This will help you a lot. Okay, for example, if you have attended the first session, go and read that part from the NCERT. If you have attended the second session, go and read that part from NCERT. So this will, make you memorize certain things, and you will also get to know that what things are important and what things you have to leave in this chapter. Okay, so that's all for today. Thank you.